Hello, everyone. I'm Rado Kalinescu. I'm professor of computer science at the University of York and the principal investigator on the research project organizing this seminar series. And I'm really delighted to introduce our speaker today, Jane Fenn. Jane has worked for BAE Systems for 33 years. She's discovered a passion for safety engineering in the early years of her career with BAE Systems, and that is something she has grown and developed both through working with the universities here at York, but also at Newcastle in a number of joint research programs, as well as through undertaking a safety engineering role within the company. She currently works with the air sector. She's driving in particular improvements in safety engineering practice, competency and training, and also engaging externally with a number of standards bodies and committees, developing guidance for safety practitioners. She also recently, in October last year, started a part-time PhD at York, looking at linking the design and in-service safety cases for autonomous systems. So over to you, Jane, if you want to share your screen.
Thank you for that. So hopefully you can now see my screen.
Yeah, we can see your screen and we can hear you well.
Thank you. So as you'll see from this, I wrote this paper with a number of colleagues. I was hoping that maybe Ganesh would be available today, but it looks like it's too early for him. He only got back to the UK. I think it was yesterday, so hope unfortunately he's not going to be able to make it, I don't think. So I'll also say that I'm currently running on a mobile phone hotspot over Bluetooth because my internet connection decided to die this morning. So if we need to turn video off to reduce bandwidth, then we'll do that as well. So I'm really happy to present this work to you today, so if I can give you a quick rundown of what we're going to talk about. So motivation and background, then we're going to talk about some architectural patterns, initially some generic ones, and then some that have been proposed specifically for AI and ML in the literature, then some conclusions and future work. So myself and Ganesh, one of the other co-authors, are actually members of a joint SAE Eurokai Standards Committee. And if you're familiar with some of the aerospace standards, obviously this is mainly aimed at an aerospace audience originally, then they produce the more familiar ARP 4754 and 4761, which are the primary safety guidance material for commercial aerospace. But within the committees, we're on a specific committee that is looking at AI in aviation. We're currently working on a document called AS6983, which will be called the process standard for development and certification approval of aeronautical safety related products implementing AI. And I do think we probably need a shorter and catchier title. So Ganesh and I were asked to write some material about system architectures that might be suitable for use with AI and ML. And while that seemed like a really simple thing to ask, we really struggled about what to write about architectural choices for AI and ML. Mainly because what was distinct, would we do differently for AI and ML than the more general architectural selection process. And we recognise that there's some specific concerns and challenges around AI and ML, but those were really context specific. So it's really difficult to formulate something that we could mandate in a standards type language other than something really mundane like think carefully. And we talked about whether we could add guidance about what needs to be considered, but again, that's tricky territory for a standard, that's supposed to be mandated for all situations. So we really struck that there'd be a gap between what we were trying to ask of people in the standard and how they might interpret it. So we felt there was a room for some explanation and some guidance, and should try and set what our expectations were about what people would do in response to the standard. So we hope that this paper would be a first step along that way in terms of asking people what we were asking people to think about. And though we've written this paper in the scope of the aerospace domain, we think that these concepts are equally applicable in other domains. And also worth saying that for some of you, this will be quite basic guidance. We see a large range of people entering this space, and particularly people who are coming from an AI developer perspective with relatively little experience in safety engineering and certification. So we've necessarily pitched this at an entry level to try and give people some guidance about thought processes and things that they need to think about, and hopefully stimulate a bit of debate too. So a little bit of background. So integrating AI and particular machine learning poses particular challenges to demonstrate that a system's safe. For example, the lack of transparency about what a system has actually learned as opposed to what you wanted it to learn. There's a specific paper that our committee produced called Statement of Concerns, if you want to read that detail. And I think it's fair to say that in our reading, we've actually found very little guidance about system level architecting, about the selection of the architecture and the optimization of those architectures. Strangely, there's actually quite a lot written about software level architecting, but much less about system level. Yet clearly the knowledge about choice of architectures is in practitioners' heads, and you know the system choices they make can be inferred from what's being captured in standards and guidance that's available, but often without a clear explanation of why they've made that choice, you know, an explanation of their rationale. For example, you know, this question of dealing with untrusted or insufficiently assured elements of a design are not unique to AI. We've spent an awful lot of time over the years in the safety community talking about what we call, commercial off-the-shelf software components, COTS components, and we've done a lot of work in assessing how we could include them in a system and still demonstrate that it's safe. So we see that evidence in published work that ML is going to have a similar impact. You know, it's a new implementation technology, and it's probably going to have as big an impact in the way that we architect our systems as it did when software was introduced. So it was kind of one of the motivations was then to look at some of the activity that we did when we introduced software many years back, and looking at whether those were appropriate analogies to consider and options to consider. So I think it's also worth saying that our specific airworthiness regulations, sorry, I have skipped an extra slide, haven't I? Okay, so yeah, we talked about the COTS components, and I think the when we're looking at the approaches to architecting in response to ML, so that these architectures that have been proposed in some of the papers that we've been reading, I think what we wanted to do is to try to explore the benefits and the risks, but also the potential pitfalls of the various different architectures that have been captured as patterns. So I think we wanted to give you our thoughts on the kind of literature that is out there and available that talks about system architecting, and to provide a little more context. So often the papers that we see written are assuming a completely top-down architectural approach, and assuming a greenfield site. So assuming that it's possible to do it top-down and there aren't any bottom-up considerations. But really the practical experience is that's not realistic. We can have many considerations that we have to take into account, and many constraints on the choices that we can make. You know, we are what we call trading off. So, you know, it's not just safety versus functional performance. There's also other what we call abilities, availability, reliability, maintainability, that kind of thing. So we're often having to trade off the choices between those. But there's also things like, you know, if we have developed a part of a system, a component, whether it's a software component or a particular part of a system, if we've developed those in the past and they have been used successfully, we may have a strong desire to reuse those, so they will constrain some of our architectural choices. So effectively what you need to do is do, I guess, what I call a thought experiment, that says we'll look in a trial and error kind of way, that says we'll experiment with potential options for architecting the system and then evaluate them and optimize them. And we've given some examples of methods that we've used. You know, ATAM and trade trees are well-known methods. Again, lots of details in the paper. Probably should have said from the beginning, this is a paper that we presented at the System Safety Symposium last week. So that's available from the SCSC website if you're a member of that, or I can put a link into the archive paper that we actually made available as well. So then going back to the aerospace domain. Sorry, was there a question?
Yeah.
No, I think it's someone who I just muted.
Thank you. So in the aerospace domain, we have regulations as well as standards, and they often provide requirements in themselves or guidance which effectively encode architectural choices in the past that have been made in the past, such as redundancy. So they can give specific examples of an architecture, or they might give you guidance about some of the criteria that you need to consider when you're doing that trade-off, such as diversity and independence. And then from a process perspective, there's a number of deviation-based safety analysis techniques, and we use these safety analysis techniques to kind of speculate about how behavior might be outside specification and how that might propagate within an architectural proposed design. There are a number of different techniques, but I guess the one that I'd most likely to reach for, which was developed in York by Dave Pumphrey, SHARD. So HAZOP, if people know that better, basically you look at all the different functions and say what would happen in omission. So if the function didn't happen, commission if the function happened when you didn't intend it to happen, and then early, late and value, which are guide words that were specifically added in as part of more use of software to describe behaviours that perhaps weren't as important in mechanical and hardware systems, but are important for software-driven systems. I think when I do this, I particularly add in sequence, which some people will interpret early and late to put a sequence in there, but not always. So I like to add sequence in for myself. So, and then once you've done that kind of analysis and done your optimization, you might come up with a design that's successful. And then if you want to use that and want to share that with others, you might call it a pattern. You might produce it as a pattern. So I'm going to talk to you in a moment about some of the patterns that have been recorded for the aerospace context. And I'm going to give you a little bit more background about that aerospace context for those who are unfamiliar. So in the commercial aerospace domain, we're set safety targets, which are typically expressed in terms of both the failure rate per operating hour or flying hour. And then for the systematic integrity requirements, we have a thing called a development assurance level that talks about the integrity requirements, and then that is used then to shape the development processes. DALE is the highest assurance requirement and DALE is the lowest. So before I move on to some practical examples, the examples we're initially going to consider were described initially in the first version of ARP 4754. If you recall earlier, I said that these are one of the fundamental safety guidance documents in commercial aerospace. The first issue of that document included some proposed architectures, and they were the time frame for that standard being released was when software was starting to become more prevalent and becoming an important part of safety protection mechanisms. So those architectures were entirely defined to look at how this new implementation technology would change the way that safety was done. So we thought it was timely to look at those again. So let me show you some initial patterns. So this first one I've really included for completeness. Some might not consider it a specific architecture in its own right. So this is the single channel. So here all the functionality is vested in that single complex function. And therefore, so all the targets, safety targets, both probability and assurance requirements are vested in that complex function too. So I guess the main challenges for this approach are twofold. Firstly, there's no current accepted way to predict failure rates per operating hour for a complex function. So often we'll talk about probability figures associated with ML, but they tend to be about the correctness, and that's not the same. Correctness is not the same as a failure rate. That's kind of an ongoing topic for discussion at the moment in our committee. Again, this difference between people coming from a safety perspective and people coming from an AI developer perspective, both talking about probabilities, and it's taken rather longer than it should have to realise that we're not talking about the same thing. We're talking about apples and oranges, and there isn't a direct translation. And that's work we're doing now to try to understand if there's an approach that works. We are aware that some systems have been certified for aerospace use, but they've been developed on a case-by-case basis, and they've only been for low-level, low assurance requirements. So really the problem areas are how we would use that in higher level, and that's a discussion that we're having in committee. The other challenges is that there is no current accepted, certainly in an aviation point of view by the regulator, no accepted approach to demonstrating high levels of assurance for ML. So in software, it's really a process-driven approach, but there isn't an equivalent currently for high levels of assurance of ML, and again, something that we're working on in the committee. So moving to this next pattern, so this is the active monitor parallel design. And I should say, if this diagram, if your instant reaction is that it looks incomplete, well, yeah, I'd agree with you. As we said, this is what was in ARP 4754. It was actually described textually in ARP 4754. And one of the criticisms of that standard was that these fragments were too simple, and they could only work if they were used in combination. So what we've done is we've taken some safety analysis of the individual fragments that were proposed in ARP 4754, and then combined them together to look at how you would build a system from that. So this first pattern assumes the monitor will see the same inputs as the complex function, but it will alert some downstream system, whatever that system might be, whether the output of the complex function is valid or not, whether it can be trusted or not. So I guess some of the primary things what we're thinking about when we're talking about patterns are things like, are they dealing with availability, or are they dealing with incorrect function? Those are the kind of two things that might be at the forefront of our minds. So this pattern doesn't in any way address availability. This is purely looking at whether it can detect and mitigate erroneous behaviour or incorrect function of the complex function. So for this pattern to work in that way, the monitor would need to understand the transfer function, would need to understand the input space for which the ML produces good outputs, and for which parts of the input space the ML outputs would need to be indicated as invalid. So when this pattern was used previously, when software was first becoming introduced, what I'm going to call normal implementation was that the monitor would provide a high assurance monitoring, and so take the highest assurance allocation, but the requirement would be split between the two parts. So for example, if the overall requirement was for DAL A and availability wasn't a safety concern for you, because we said this doesn't address availability, then the software or the complex function in this case could be DAL-C, providing the monitor was at DAL-A. So that in itself gives us some issues with the complexity of understanding the input space for which the monitor has to flag the complex function output as invalid. We would need to know that mapping and that transfer function to a level that's sufficient to support the high assurance DAL-A monitoring function. So, you know, in some of the software and in some people's mental models of how ML works, they might just think that's an out of bounds check. An out of bounds, certainly that it's reasonable to assume we could do those at high assurance, but depending on the type of ML function that we're talking about, which could be quite complex in itself, the areas, things like instability and lack of generalization, if though that's a complex transfer function, achieving that understanding of that complex mapping may be quite difficult in its own right. And again, achieving it to that high assurance is likely to be difficult. So the second pattern is the backup parallel. Again, opposite to our last pattern. This one is focused at availability, but doesn't do anything to help us with erroneous behavior. So when we looked at introducing these patterns for software, the expectation was that the backup function may be simpler and lower, and then could be lower assurance. So for a DAL-A system, the primary portion might have been level A and the backup could be level C. But I think based on our concerns about the difficulty of achieving high assurance requirements for ML, with ML, what we'd likely to do is would reverse that. So we'd make the primary function, that's the complex ML function, the lower assurance requirement, and the backup function that's implemented in more traditional techniques, the higher assurance part. And again, the immediate challenge here is that given that original intent that the software function was capable of determining when it had failed and signaling the backup to take over. So now we've swapped those assurance requirements, we've now got a low assurance ML system, even though it might be the preferred functional, might be the preferred option functionally. We're now relying on the low assurance ML to tell us when it's failed. So also being low assurance, we would anticipate that ML would fail more often than a high assurance function was. So we're also going to be in a situation where we're running more often with the backup function in control rather than the complex function. So you would need to, in context of what your function is delivering, you would need to decide whether running on that backup function, which could be, you know, sort of equivalent of a get you home type capability, whether that is sufficiently safe for that to be the predominating functional availability. So that needs to be decided in context. So next we've moved on to combining those last two patterns. So we have assumed that loss of function is inherently more easy to detect externally. So we've really focused on this erroneous function as the main driver. So we've retained the high assurance backup function for availability reasons. And we showed that an external switch of some type would be controlled by the monitor and select the correct output, either from the complex ML function or from the backup function. But unfortunately, in this variant, we still retain the issue of the ML self-diagnosing and reporting its error. And the monitor still needs to understand this transfer function to determine when to switch over to the backup function. So the paper takes you through a number of these different options. I just showed another couple there. Now, I don't propose to go through these in a huge amount of detail. You know, give you the link to the paper so you can read more detail if you want to. But one of the interesting things on the pattern on the right-hand side, we have one of the things that came out of the analysis of this is the effect of timing behaviours. So if we're asking the monitor, so the monitor is independently sensing the external environment to determine whether the inputs would cause a problem to the ML function. what we were thinking about was the fact that if the monitor is high assurance and being implemented in traditional hardware and software, the timing behavior of that monitoring is has the potential to be slower, most likely slower than a complex optimized ML system working on dedicated, bespoke, fast hardware. So, you know, are we going to end up with a time where there's some kind of race condition where the monitor is unable to switch the output to the safe backup because the ML function had more quickly created that incorrect and invalid output? So all sorts of interesting things coming out of that. This is the point where I was hoping that Ganesh would be around, because this was the work he did. But I'll talk you through what I can, and hopefully people won't ask me difficult questions about it. These are some of the patterns that we picked out from papers that have been produced in this area. So there's runtime assurance. So there's actually a standard that defines that, which is the ASTM F3269, which has been updated in 21. But there are other variants around this. So this is similar to some of the variations that we've just looked at, those combined patterns, and has some of the same issues about whether the backup function is as acceptable, suitable, is a problem if that's in control, if it has a limited functionality. So again, the same problems that we were talking about, this complex function boundary, this assurance requirements, the way that we allocated them. So one of the things that, again, in the paper that Ganesh has gone into, we looked at the complex function itself is actually made up of pre and post processing, as well as the ML model itself. And those are likely to be done in traditional methods rather than in ML. So how you allocate the requirements, the DAL requirement to those pre and post processing parts, and what's inside the DAL allocation, what's outside it, so that there's some interesting work in there. We also looked at whether we can claim any credit if the monitor is actually learning in an ML sense the limits and boundaries on which the main function is not operating appropriately. So do we get some trade-off if we've got learnt monitoring as well as learnt complex functions? We also looked at the potential for ensemble learning. So if the complex function was actually made up of smaller models that work together, would there be opportunity to put monitoring points in between models to help with simplify that monitoring function? So the other one one of the other ones we looked at was value overriding. So this is where the ML is being fed with sense data and levels of uncertainty around that data. And then the expectation would be that if a threshold value of uncertainty is met, is exceeded, then a safe, whatever safe means, value could be substituted instead. And then that level of overriding was dependent on the operations situation. It's in there somewhere. That it was in, whether it was a high risk or a low risk situation might be, you could fine tune that overriding for that kind of situation. I think our concern was that there are specific requirements in the regulation that talk about fail-safe design principles, and we were concerned as to whether some of the safety margin reduction that was being proposed for performance gains would be in conflict with that regulation. So there's certainly some regulatory conflict potentially there for the aerospace domain, but really there was challenges about, you know, this defining what these safe values would be, and if that's something that's actually doable, and the uncertainty distributions, how assured we could be about being able to map those and understand those, and understand the estimates of uncertainty, what level of assurance we had with that uncertainty. So this thing about operating situations, again, what level of confidence could we have in the detection of that operating situation to be able to then do the variation of the risk situation and the level to which we could override values. There are other patterns. These are not my speciality. I get as they go on, I have less experience with them. Again, this function modification, can we do something post processing to enforce some kind of safe value? This is again something that's been proposed in the automotive industry about localization of bounding boxes on visual processing. For example, whether we could do something there that changes the size of the bounding box to give us a confidence that the actual what we've detected would be inside the bounding box. That interesting perspective, but it really only works for true positives. So, you know, if part of the problem is that we're worried about the false detections, then this isn't helping as much. So I think it has some potential, but I think that there are significant problems with it. All the same things that we've had before about the self-checking and the detection of the out of bounds or the bounding issues. And I think this was the one that kind of made us stop and think a little bit, because this is one that's been used in practice. It's input partitioning selection, so it's a multiplexer input and a demultiplexer on the output. So you actually effectively split up the operating domain into a number of different complex functions, of which at least one must be a safe alternative traditional implementation. So that can be the higher assurance one. Again, this is not helping us with erroneous. This is helping us. This is dealing with not dealing with availability, because if you lose one of these channels, then you've lost the function in that part of the operating domain. So and again, we get into the issue where the monitor will need to be high assurance to be able to switch between the appropriate channel for the range of the OOD that we're actually wanting to process, and that the inputs are correctly routed into the output. And again, we've got this thing, if we want to make the conventional software the higher assurance, we've got the it would need to be fully functionally equivalent rather than the get you home capability. So and because of the way it's done, we would still have the whole of the safety assurance requirement, the DAL requirement on across each of the channels. So we see the ambition, but we see probably more complications on that one. So I guess just to wrap up, as far as we're aware, this is the first paper looking at architectural patterns from a safety viewpoint when integrating ML. We've not tried and we've not attempted, and we don't recognise it's not a comprehensive study of all the known patterns. We have analysed it from a safety standpoint. We have seen some patterns looked at from a safety standpoint, but they didn't consider the ML-AI integration. So we've looked at whether the comments that we've raised would be appropriate for other domains. So, you know, in automotive, where they have the ASILs and SILs in IEC, whether those might be equivalent to what the debates we've had about DALs. We think that there may be some read across so in those other domains. And we have looked at the existing architectural patterns that were recorded in the ARP, and we think that there is some potential to reuse those patterns, but we'd need to modify the recommendations if we were introducing AI ML into those patterns. We think that we need more careful assessment of the new patterns if we want to start using them in higher assurance applications. So the stringency of the DAL requirements, some of the high criticality needs mean that any implementation using these patterns is going to be very costly and effort intensive. And some patterns may not be suitable at all. The value overriding, we were struggling to understand how we could use that effectively. So so for some patterns, when we look at if the monitor is going to be as complex as the ML, why would you? And you have to implement the monitor in traditional software. Then what's the benefit of having the ML in the first place? So that there are some key areas that there are trade-offs, and we need to start thinking about the trade-offs in there. And safety is going to continue to be a major challenge for them. So as I say, we were hoping that this would prompt some debate predominantly. So in terms of future work, we think that there's activity required to do more comprehensive analysis of other patterns used in aviation. There are some predetermined architectures out there that are quite common in aviation at the moment, like IMA, FACE and CAS, which will constrain some of the again, this architecting a greenfield site, there isn't quite a greenfield site, that there are some predetermined options that you might need to comply with. And we think that there's definitely room for an architectural patterns catalogue and an assessment framework for those architectural patterns. So, some of the points that we've brought up, how can we structure those in a way that's useful and productive for people who want to adopt those patterns, and so they can understand what they ought to be considering if they're going to use them at different assurance requirements. And we think potentially that there is also a place for either an assurance case or particularly a confidence case pattern catalogue to accompany those architectural patterns. Okay, so that's kind of all I had. Happy to take some questions.
Thank you very much, Jane, for the insightful talk. I certainly learned a lot from it, and I guess I would like to invite questions if people have.
I have a question.
Please.
Hi, Jane, it's Colin.
Hiya.
So I think the answer to this question was in your last slide, but I just wanted to clarify. You were talking about an assessment framework for patterns. So I was wondering, in your paper, do you start to tease out a methodology for doing such an assessment based on what the patterns you've already analysed?
Sadly, we hit 25 pages on the paper and hadn't got that far. We had hoped to start doing that, but we kind of ran out of space to do that. That there are a number of papers that we found that had created assessment frameworks, predominantly in the software area. So we think that it shouldn't be too difficult to pull those ideas together, but wasn't something that we had time for, unfortunately.
Okay, thank you.
Right. Any other questions? So before other people come up with questions, I wanted to ask something about reusability. So often it feels to us, at least within the Assuring Autonomy program, that one challenge with ML AI components is that, unlike some of the traditional software, all this effort that is put into their assurance could easily be lost if you move to, I don't know, another operational design domain or another type of airplane, I suppose, in the context of your presentation. Is that something of concern as well, do you think, to the difficulty of reusing components?
Yeah, it's not something that we had time to look into, but I have been noticing the research that's been looking at transfer learning, that whether you can, obviously you can freeze whatever term you want to use the learning at a point to release a component into a system, which is something that we need from a regulatory point of view at the moment. That's something that the regulators are demanding, that systems don't learn in service. But yes, on that basis, there's a very much a vested interest in understanding the mechanisms for that, and the mechanisms that we can then transfer that in across a whole fleet of aircraft that are using the same ML. And if we make an update, then the change management will be really necessary. So I think from many different points of view, both the reuse and the change management in service, we need to understand what the options are for preserving that learning and a known amount of learning as well, so that we can use that in our recertification effort. I'm not sure we're there yet, but it's definitely something that I'm aware of is in progress. Not too involved with it, something I know I'm going to have to get involved with as part of my PhD.
And thank you, Jane. Janaina?
Oh, Jane, thank you very much for a very insightful presentation, and I've learned a lot with that. So yeah, I have actually a couple of questions. So since you have an architecture that is driven by the properties, so I was wondering if among those properties, time bound was a concern in there, and also, I was wondering about the generalizability, the ability to generalize those patterns, in the sense that cyber physical systems probably would benefit from those patterns that you have explored there, and potentially using frameworks like Simulink or Open Modelica to exercise them and to see even if the integrability of those components, they would come up with those properties in a safe manner. So there are two questions. So if you want, I can repeat them. So
I think the first one was about time bound, and it's a very good question. I guess at system level, or we tend to think less about that at system level than is done at software level, but it is something that we need to be aware of, and certainly, some of the things I was saying about the different timing performance behaviors. If we have a monitor that's monitoring something that is ML but isn't itself ML, whether there'll be race conditions with that. So we do need to think about it. I'm not sure we have in the past, when we have looked at architectures at that level, been too cognizant of what the importance of timing behavior, but I think it's something that we should be. But certainly an awful lot of the ATAM method that I mentioned, that was initially developed for software systems, and timing behavior and timing properties was one of the first things that they looked at as part of it. So yeah, it's something that I'd certainly encourage people to be considering at architectural level. And then in terms of the remind me of the second question.
Yeah, the ability to use some frameworks that people already do some verification, or at least to do some to integrate with those simulation environments to help you to anticipate some of potential failures that can come from your decision, from your architectural decision. So, for example, in the way that we do, for example, static analysis, or even the way that we can assess modularity from architecture, I believe that when you build those complex systems, avionics systems, you might need also to provide some guidance if you're not doing something wrong when you devise your architecture or when you instantiate your architecture. And then probably these people, they use the simulation tools like OpenModelica or Simulink or stuff like that. So how we could maybe generalize the way that you extract those patterns, or even if not able to generalize or even integrate with those simulation tools, so people can have assessment of their architecture from qualitative perspective, using the tools that you already use in their environment.
Yeah, many ideas in that. So yeah, so I think from my perspective, one of the things that I would love to do is talking about ATAM. It's a really deceptively simple method, and I would really love to be able to do architectural optimization in the simulation. So I think that it would really lend itself to that. I've not seen it done. I've suggested it to a couple of people, and because practice is somewhat behind what is the state of the art, our aviation systems have been relatively simple. They're taking a huge step change at the moment in the level of complexity of our aviation systems from an architectural perspective. And I think that's the kind of thing that we should be doing to make our architectural selections. We should be simulating them and evaluating them. It's at the moment it's a pipe dream rather than a reality, but that's certainly an area that I would have an interest in. And I think one of the other things that does worry me, that a lot of the research I see at the moment is kind of stovepiped around assuming that the ML is the whole system. And kind of when we use them in practice, it isn't the whole of the system. So, you know, if we have got some really high assurance verification activity happening in the ML part of the model, how it links into the rest of the world, and how we can get the benefits of that when we're using that in context of something that's implemented in traditional hardware and software, that does worry me a lot, and I think that's something that we as industry we need help with, and we need help to understand what would be the best way to optimize the benefits that we get, because certainly my feeling is that industry isn't going to accept developing the whole of our aviation systems in formal methods. So there has to be some boundaries and some frameworks to make those things work together. So yeah, I'm very, very interested. Don't have a solution though.
Okay, excellent. Because this is really hard to assess the quality of an architecture, even for relatively simple software systems. Imagine that magnitude. So thank you for a very thorough answer. Thank you, Jane.
Thank you.
Grisel, would you like to ask your questions?
Yes, hi, very interesting talk. Nice to see you again, Jane. Hi. I have two questions. The first one is, maybe I missed it, but respect to development assurance levels, is this like a discrete scale that is out there, or
yeah, it's quantized. There's just eight levels, and there are process markers for each of those different levels. It's kind of an old-fashioned way of doing things, but it's kind of the best that aviation has at the moment.
Okay, and my second question is, when you refer to these patterns applied to aviation systems, the aviation system is too general, so I was wondering if these are applied to a specific system in the aviation, in aviation, or are these different parts of the system within the aviation or within a plane?
So the way that the aviation, the ARP standards are set out, they define an aircraft level, a system level, a subsystem level, and potentially the patterns could be applied at any of those levels. But the underpinning requirement for the in the ARPs is that if we're going to do this split and try to reduce the effectively the assurance burden, because developing something to a high assurance can be very, very expensive. If we're going to try to take some advantage of the architectural approach to reduce that burden, then we are allowed to do that once. So it could be applied at many different levels. Probably it's going to be at subsystem or system level. Most likely it will be applied.
Okay, thank you.
Okay.
I do have another question as well, Jane. So from what you described, and you already answered this to some extent, the patterns and their analysis is currently a bit of a thought experiment. Well, what do you think is, how does the path look like that will take us from these thought experiments to actually deploying the patterns in practice? Do we need to go through lab experiments? How would that work?
I think, as I said, simulation would be the ideal for me. I'd kind of have a perverse pleasure in having ML decide on the pattern that the ML lives in. Current practice and current practice is rather limited on what architectural trade-off it actually does anyway. But it's all very mandrolic. It's about identifying that optimization, which is largely done manually at the system level, and then then being manually transferred into a design tool. So the option to be able to model those architectural options, then simulate them, and record our rationale and our choices and the different results that we got from simulation experiments, to be able to preserve that information in our design models as we take them forward. That would be really good. At the moment, I think practice has got some catching up to do in terms of actually how we use these kind of techniques, other than the manual processing that we do now.
Thank you. Tim?
Oh, thanks, Jane, for a very interesting presentation. If I can, would like to take you back to one of the statements right at the start, which was the distinction between failure and correctness. I've got a perhaps slightly simplistic model in my mind from doing traditional algorithms most of my career. And our thinking has been to tend to distinguish between failures of the software to actually deliver the result that it should have delivered, failures of the algorithm, which could be statistically based or might actually be direct calculation. But if it's a statistically based one, you've got the probability that it's actually chosen the wrong answer. It's a false positive or a false negative, for example. And then you've got what I think is the third category that you're bringing in, which is what does the rest of the system do with the answer and how does that behave? But I suspect that might be a way too simplistic approach given what you've described, and given that ML brings in yet another one, which is how good has been the learning and the data that's gone into the learning and all of the rest of those questions. I just wonder if you'd like to elaborate a bit more on that subject and how we really should be thinking about breaking down the problem so that we analyze it properly.
Yeah, it's a good point. So I think so a diagram that I was showed in the committee really changed the way I thought about the failures and the erroneous behavior. So how to describe a diagram in just in words. So if you might imagine a straight line transfer function, that's what was intended. But if the ML hasn't learnt, hasn't been provided with the data, hasn't learnt as well as we would like, then in certain parts of that distribution, we might have something where a small change in the input creates huge changes in the output. And kind of that's what they would class as instability. So, you know, in a software function, we talked about the traditional software, we talked about them, there might be huge step changes in the range. You can't assume a linear progression between different test points as we had done for hardware systems. You get that amplified in ML systems, and a very small change in an input could create huge changes in the output. So I was talking to somebody after the SSS presentation last week, and you know, he was saying to me, so if you have two identical algorithms that have been fed with identical data and you're giving them the same inputs, will they always come out with the same answer? And the reality is no, because you know, within a system context and slight timing behaviors and inputs and outputs, if you're in that area of instability, you are going to have huge differences in against the output you might have expected. And there is only so much that the developers at this point can do to fix that problem. So we will have to create safety behavior and safety functions around that lack of stability, for example, in that in an area that we're wanting to use the output of that ML. So that's why I say complex functions. It's a complex function to understand that transfer function in its own right.
Yes, now understand. Yeah, we have seen instability coming from just regular regression without any ML involved, of relatively simple functions where you're taking the regress data and using that to compute something else. And we've then seen significant variation in that something else as a consequence of possibly moderately significant changes in the terms that have been derived by the regression, but such small changes that they're extremely difficult to detect in that initial regression.
Yeah.
And that's the sort of thing you're talking about with the ML there, isn't it?
Yeah.
Yeah. Yeah, I understand. Whereas to you, a failure is something that's wrong in the way it's been processed. Would that be a fair statement?
Well, I was trying to be a little careful at the beginning. So saying behavior outside its intended specification.
Yeah, I'm with you.
Cover all.
No, really interesting.
Thank you.
It's educational for me because we don't deal in AI or ML.
Okay.
Thank you.
Right, so I think we reached the end of the today's seminar. Thank you again so much, Jane, for the thought-provoking presentation, and thank you everyone for the questions and participating in the discussion. See you in 2 weeks' time. Thank you.
Thank you.